for the procedure exercises, and then for the principal exercises, I'm going to do the 2 in the TUT. Right. So this is TUT 8. So the procedure exercises. So the first question, all of the questions under the procedure exercises are just to find the inverses. Right, so find the inverse if it exists. And the exercises are all from section 3.3. Right. So the first one I'm going to do is number 2 from section 3.3, and it says that we have to find the inverse of the matrix 4 minus 2, 2, 0. So this is just a little bit of revision of how to find the inverse. So this is a nice and easy one because it's 2 by 2, and in general when we have a 2 by 2 matrix A, B, C, D, the inverse of that matrix is going to be 1 over AB minus BC, and then we are going to switch around our A and D, and we are going to change the signs of C and B. So for this matrix, the inverse is going to be 1 over 4 times 0, so it's 0, minus 2 times 2, and then we have our matrix, so we're going to swap the 4 and the 0, and we're going to change the signs of the 2 2's. So it's 2 is going to become minus 2, and the minus 2 is going to become 2. So this is 1 over 4, 0 to minus 2, 4, and then I'm just going to multiply in that 1 over 4 to get 0, a half, minus a half, and 1. And you can always check whether your inverse is correct by multiplying it by your original matrix and checking that you do get the identity matrix. The next one I'm going to do is number 55. And this one actually says that we have to use our Gauss-Jordan method for finding the inverse. So use the Gauss-Jordan method. The matrix looks like this. We have A1, 0, 0, A1, 0, 0, A, and then when we use the Gauss-Jordan method, what we do is on the right, we write a identity matrix with the same size as the identity matrix on the left. So it's 1, 0, 0, 0, 1, 0, 0, 0, 1. And then what we have to do is we have to perform elementary row operations on this entire matrix so that the left side becomes the identity matrix. And then whatever we have on the right will be our inverse. Right? So please check these operations while I'm writing them out. And please tell me if I make a mistake. Right? So the first thing that I'm going to do, remember you can choose your own order of operations as long as your final result is that you have the identity matrix on the left. So I'm just switching rows 1 and 2. So that I can have a 1 in my top left hand corner. Then I have 1, A, 0, 0, 1, 0. A, 0, 0, 1, 0, 0, 0, 1, A, 0, 0, 1. below my first leading one. This is my first leading one, so I want all zeros below it. So I'm going to say row 2 minus A times row 1 to give me the new row 2. So my row 1 stays the same. For my row 2, I'm going to have a 0 here. Then I'm going to have 0 minus A times A. So it's going to be minus A squared. Then I'm going to have 0 minus 0, so it's just 0. Then I'm going to have 1 minus 0, so it's just 1. Then I'm going to have 0 minus A, so that's going to be just minus A. And then 0 minus 0 is 0. And then I'm just writing my third row down. What I'm going to do now is I'm going to swap rows 2 and 3. Because then I'm going to get my second leading one into the position that I wanted, which is here. Right, so we are swapping rows 2 and 3. Did I say 2 and 1 or 2 and 3? I meant 2 and 3 if I said 2 and 1. So first row stays the same. Then I have 0, 1, then I wrote that A as a 0. It's supposed to be an A. Sorry guys, so this one I wrote as a 0, but it's an A. I just rewrote it incorrectly. So I'm swapping the 2 rows now, so it's A, 0, 0, 1, and then I have 0 minus A squared, 0, 1 minus A, and 0. Now what I want is I have my second leading one, so I want all zeros below and above it. So I'm going to say row 1 minus A times row 2 to give me the new row 1. So let's see what we get there. So that's going to be 1, and then we have A minus A, which is 0, and then we have 0 minus A squared, so it's minus A squared. Then we have 0 minus 0, which is 0, 1 minus 0, which is 1, and then we have 0 minus 1 times A, so it's minus A. In my second row, I'm leaving it as it is. And my third row, I'm going to add A squared times row 2 to it. So then I have 0, 0, 0 plus A times A squared, so that's A cubed. 1 plus 0 minus A plus 0, and then 0 plus 1 times A squared, so it's A squared. Only 2 more steps, almost there. So the next thing I'm going to do is I'm just going to change my A cubed to a 1, so that I have my third leading one by multiplying row 3 by 1 over A cubed. So my first 2 rows stay the same. And then my third row is going to be 0, 0, 1. Then I have 1 over A cubed minus 1 over A squared and 1 over A. And now all I need to do is I need to create all zeros below my third leading one. So I'm going to say row 1 plus A squared times row 3 give me the new row 1. So then I get 1, 0, 0. Then it's going to be 1 over A, 0, 0. And then I'm going to say row 2 minus A row 3 to give me the new row 2. So then I have 0, 1, 0, minus 1 over A squared, minus 1 over A, 0, and my third row stays the same. So that means that the inverse of the matrix that we started with is this matrix that we have here. So it's 1 over A minus 1 over A squared, 1 over A cubed, 0 minus 1 over A, minus 1 over A squared, 0, 0, 1 over A. And you can check that that is correct. I haven't checked, so I hope it's correct. You can just double check that. Then the next one I'm going to look at, I'm just doing a simple one of these because there is one in the TUT where they ask you to get the inverse over Z5. I'm just going to do 1 over Z2, but you are not being examined on this, right? So that's why I don't want to focus on it. But in number 60, they asked us to find the inverse of this over Z2, right? So in Z2, the thing is that we only have addition and multiplication defined. We don't have subtraction or division defined. So we can get our inverse by only doing addition and multiplication. So I'm going to do the same thing as I did before by just writing it into an augmented matrix where I have the identity matrix on the right. So the first thing I'm going to do is I'm going to swap my two rows because I want a leading one in the top left. So it's 1, 1, 0, 1, and 0, 1, 0, 0, 1, 1, 0. So now all I want to do is I just need to get that to be a 0, right? And how I do that is I can say, so remember I can't subtract, but I can add. So when I add 1 to 1, what is 1 plus 1 in Z2? 2. Yes, 0. Because if we divide by 2, the remainder is 0. And it's equal to whatever the remainder is in Z2. So we have row 1 plus row 2 to give me the new row 1. Row 2 stays the same. So I'm going to have 1 plus 0, which is 1. 1 plus 1, which is 2. But when we don't have a 2 in Z2, we only have a 0 and a 1. Those are only two elements. So the remainder, when we divide 2 by 2 is 0, so that's a 0. 0 plus 1 is 1, 1 plus 0 is 1. And then my second row remains the same. So this matrix here is the inverse. Do you guys have any questions about finding the inverse? So now I'm going to do the two principal exercises as they are in the TUT. A1, A2, up to AN are invertible matrices of the same size then their product is invertible and the inverse of the product, so it's A1 times A2 up to AN inverse is going to be the inverse or the product of the inverses but in the reverse order. So AN's inverse down to A2's inverse, A1's inverse. Right. So we want to prove that by induction. So in the section 3.3, we already showed that this property holds for two matrices. We did a proof to show that it holds for two matrices. So I'm not going to redo that. So we're just going to use the fact that it holds for two matrices in this proof. So I'm going to make my base case when n equals 2, because then I have the product of two matrices. So if n equals 2, then the inverse of the product of A1 and A2 is A2's inverse times A1's inverse. So this was from the properties of invertible matrices. Theorem. In section 3.3, and it was number 3. So there we proved that it holds for the 2x2 case. Or not the 2x2 case, for two matrices. Now, our next step of induction is to assume that it's true when n equals k. So, assume true for n equals k, and that is going to be our induction hypothesis. So in other words, we are going to assume that the inverse of the product of k matrices equals the product of the inverses of the k matrices in reverse order. And now we just need to prove that it is true when n equals k plus 1. So prove that it's true for n equals k plus 1. So on the left, I'm going to write down my k plus 1 matrices, the product of them. And I'm going to work out the inverse of this. So what I'm going to do is I'm just going to group these two matrices together as one in my next step. So I have A1, A2 up to AK plus 1, but I group those two together and I'm looking for its inverse. So what I have here now is I have the product of k matrices. So this is one matrix now. I'm looking at it as one matrix. Right. And in our induction hypothesis, we showed that the property that we are trying to prove is true does hold for k matrices, right? So we can use our induction hypothesis and we can write this as the reverse product of the inverses of those k matrices. So this is my first or my last matrix, which I'm now going to write first. Its inverse, and then we go down to A2's inverse multiplied by A1's inverse. And we also know that the product or the inverse of the product of two matrices is the product of the inverses of those two in reverse order. That was our base case. Right? So in our next step, I'm now going to write this inverse as the product of two inverses by swapping the order. And then I still have A2's inverse, A1's inverse, and that's what I wanted to prove. So all we did was we just used the fact that we know it holds for two matrices because we've proven that in the theorem in section 3.3. Then we assumed it's true for k matrices. Then we changed our k plus 1 matrices so that it's k matrices by just grouping two of them together. Then since it's k matrices, we can use our induction hypothesis and say that the inverse of this product is the reverse product of the inverses. And now what we have is the reverse product of the inverses, but here in our first place we still have the product of two matrices. But we know that it holds for two matrices, the property that we can swap the order around if we want to write it as a product of inverses. So from here to here I just swap that order around, and then I had what I wanted. I wanted to show that the inverse of the product of k plus 1 matrices is the product of the inverses of k plus 1 matrices. Do you guys follow that? Any questions about that? Right. Then, the next one, number 5. Say, a square matrix is said to be idempotent. I'm not sure how to pronounce it. If a square equals a, right? Prove that the only invertible idempotent n by n matrix is the identity matrix. So I'm going to do this proof in two ways, just so that you can see two different proofs, but they'll short. Right. So what I want to prove is I want to prove that if a squared equals a for an n by n matrix, then a has to be the identity matrix. A has to be I. So I'm going to start with the property that a squared equals a, because we are working with an idempotent matrix, and now we just want to start from there, start from the property of it. Now what I'm going to do is I'm just switching the a and the a squared around just for my own sake, because I have to switch around my notes, so otherwise I'm going to get confused. Now I'm going to multiply on both sides of my equation with a's inverse. So here I have a, and I'm just writing this a squared as a times a. Then I'm going to group these two together, A's inverse times A. And on the left, I also have A's inverse times A. So I have identity on the left equals identity times A. And identity times A is just A. So A is the identity matrix. And that's what we wanted to prove. Sometimes these proofs seem like they are so straightforward. It's actually like, it doesn't even make sense that it's that easy. You feel like it should be complicated. You guys get the steps there. All I did was I just multiplied both sides by A's inverse. That's all I did. And then that proved it. Another way is, so this is proof 1, proof 2. So we start with A equals A squared again. Then we can write this as A squared minus A equals 0. Then I can take out a common factor of A. Because remember that matrix multiplication is distributive. So this is just the reverse of distributing. I can take out a common factor of A. Then, once again, I'm going to multiply with A's inverse on both sides. And now on the left, I'm going to group the A's inverse and A together. So what I have then is I have the identity matrix multiplied by A minus I equals, and any matrix multiplied by the zero matrix, so that's the zero matrix, is just the zero matrix. And the identity matrix multiplied by any matrix is just that matrix itself. So this is just A minus I equals 0. And that means that A equals